Hello folks, I'm Sachin Ashok and today I'll be presenting the TraceWeaver project, which is about enabling distributed request tracing for microservices without any application modification. I'm a graduate student at UIUC and this is joint work with collaborators from UIUC and IBM. We begin by observing the evolution of software. Traditionally, software systems were monolithic with components communicating through direct function calls. Today, the need for scalability and easier deployment has led to microservice architectures where modular components communicate via network calls instead of function calls. All that is great, but the problem is that debugging in such a microservice style architecture can be extremely difficult. Consider a microservice system as shown here, which receives a few requests it needs to service. Typically, these requests move from one service to the next, following a very convoluted path, creating a big observability challenge. Fundamentally, this is because many complex services must interact with each other to produce even a single end-to-end response. As a more concrete example, here is a visualization of how services are interconnected at Uber. Chasing the long tail latency for requests is difficult because the execution traverses many hops and have many complicated dependencies, and therefore you need visibility across these multiple services to understand the processing of even a single request. And this is exactly where end-to-end request tracing comes in, but let me give you a brief primer. In tracing, a request along with its response is called a span. It is an individual unit of work which starts with the request arriving and ends with the corresponding response being sent out. Please note I'll be using request and span interchangeably from here on. Now in this microservice, we have two requests, or let's say spans, arriving at the front end, yellow and red. All the yellow rectangles here are individual spans which together constitute an overall end-to-end trace. The job of end-to-end tracing is to stitch together these spans to create a coherent trace of execution. Such traces provide us with a lot of visibility, which can be quite useful as it can answer many interesting queries like which service contributes most to the delay experienced by the slowest 1 to 2% of the requests, or which client requests are causing out-of-memory errors at service X, or how much time did high priority requests take at a particular service. By the way, end-to-end tracing is only one approach and there are other related debugging strategies in this space. There is service dependency mapping, where the goal is to infer coarser service dependencies like the fact that A depends on B and C, while B and C do not depend on A. There's also span and service level analysis, where you can analyze these fragmented spans to ask questions like how long did this individual span take at a service. However, both these approaches are not sufficient for the kind of queries we mentioned before. This is because the first approach of service dependency mapping cannot do finer-grained request level tracing, and the second approach of span level analysis, while being fine-grained, cannot do any end-to-end analysis. So it sounds like end-to-end traces are great to have. So then what's the challenge with getting such traces? The fundamental challenge is the following. So let's say you have a couple of incoming requests arriving at your front end. Now, in order to service them, the front end might issue a couple of backend requests. The fundamental challenge lies in trying to map these incoming requests to the backend requests. For example, is this the right mapping, or is this the right mapping? Without knowing what's going on within the application, this is very hard to say. And this problem is replicated in every single service the requests interact with. Mapping these incoming requests to the backend requests at every single service is the main challenge in end-to-end tracing. Currently, the standard way to achieve end-to-end request tracing is via header propagation. In this approach, when new requests arrive, the gateway generates and adds global IDs. When backend requests are generated, these global IDs are replicated and propagated across subsequent related requests via headers by all the intermediate services. The problem with such an approach is that it involves cooperation across every single component of a distributed system to instrument their code to add these headers, and therefore for large applications requires buy-in from hundreds of loosely coupled services, which can be quite hard. In this example, we see 6 services that are willing to modify their code and add instrumentation. Please note, adding instrumentation is usually at the bottom of the to-do list for developers, but even if they're willing to invest time into it, it can be quite tricky since every single function signature needs to be modified to carry the context of where the request originated. And even when multiple applications can be modified, you still have others which are legacy or proprietary applications which are very hard to modify. For all these reasons, header propagation can be a pain, resulting in a low rate of deployment in the industry. So given how much of a pain header propagation is, we ask the question, can we enable approximate end-to-end request tracing without application modification? We say approximate because even approximate tracing is already good enough for a lot of use cases. So at a high level, the general approach we follow is to ask what data is externally observable or can be inferred within this environment. Then we run joint optimization to output mappings in a way that is consistent with all the observed data. Now we'll iterate through a list of information that we identify to be generally observable or can be inferred without modifying applications. I'll next go into each of these items individually. Just to elaborate, the reason we are interested in getting information like this is to be able to use that information to aid in mapping an incoming span to an outgoing span. The more information we have available that can hint at which outgoing span is the right one, the better the tracing accuracy will be. So for example, the first kind of information is the request response timings, such as T1, which is when the request arrives, and T6, which is when its response goes out. We can use any sort of middleware which can intercept a stream of requests to log the timestamps. We use eBPF to get this information, but a service mesh proxy, a Wireshark or TCP agent are all equally good candidates to get this data. Next, we also infer the request to response mappings. Recall that a span is comprised of a request and its associated response. When we say that we're working with spans, this is because the mapping of a request to its response is inherently known if the protocol used by the request is known. So for example, for a HTTP2 flow, a protocol parser knows that the requests and the responses within a single HTTP2 stream are associated in FCFS order. Please note that this does not solve the mapping problem, as we can only map requests to responses using protocol knowledge to form spans. But we cannot then map these parent spans to their child spans as shown in the figure, as they're part of distinctly separate HTTP2 connections. Next is the call graph. The call graph is essentially the path we expect the execution of a request to take. So for example, for the execution of a single request of a particular type, the request might traverse only a subset of services as shown by the red lines. We use the API endpoint a request hits to classify a request to be of a particular type. And we call the set of services invoked to be the call graph. This information is critical since it tells us requests coming from which service should be related to requests going to which other services. And it also tells us that, for example, service X after receiving a request does not call service Y, so we can use that information to rule out making any mappings between X and Y for the requests of this type. But these call graphs are usually hard to identify when there are many concurrent requests in the system. So what we do is we run requests one at a time in a developer environment to obtain this information. Since in a setting with no other requests to introduce ambiguity, we can observe the call graph of a single request correctly. Next, we infer some causality constraints. We identify two types of constraints. The first is the parent-child constraint. To illustrate, in the figure, the blue span is represented by a larger rectangle for the request and a smaller rectangle for its response. The flow of time is shown on the y-axis. Parent-child causality enforces that the request in the parent span must arrive before the request in the child span, which is the red span, is sent out. Similarly, the response for the parent span should depart only after the response for the child span has arrived. Now, the second set of constraints are the sibling constraints, which is simply enforcing in what order the backend calls should be made. So in this case, the call to B must start and finish before the call to C is made, which is in contrast to a constraint which allows those calls to be made in parallel. To obtain these constraints, we can use the traces generated in the developer environment mentioned previously. We call these test traces, and by analyzing these test traces, we can infer these constraints. Here we show why constraints are useful to know. So imagine you have three incoming spans as shown, red, blue, and green. The backend spans are in gray since we do not know a priori which backend span was caused due to which incoming span. But what the parent-child constraint allows us to do is to say with the guarantee that the green span cannot be mapped to the third gray span, as the response for that third gray span arrives after the response of the green span has already gone out to the client. So essentially, such constraints allow us to prune candidates. Finally, we also construct interspan time distributions, which is basically our estimate of the processing time between receiving a parent request and sending out its associated child request. So for example, what is the expected time gap between a request arriving at service A from a user and sending out a child request to service B? This is useful because if we have many child requests or spans which satisfy the constraints, which we call our candidates, we need a way to rank these candidates in terms of likelihood, which is where these probability distributions are useful. We obtain these through an iterative joint optimization process, which is explained next. An iterative joint optimization process is required because we have an interesting chicken and egg problem, which is that we want time distributions to create mappings, but we need mappings to even build time distributions to begin with. To solve this, we start with a best guess seed distribution, which it does not use mappings as mentioned in our paper. Then we iteratively improve the distribution by applying the other techniques to improve the span mappings. Then we take those mappings and construct the distributions for the next iteration from it. In a sense, what we're doing is jointly learning the distribution and the mappings. Finally, we run our joint optimization process, which outputs a set of span-to-span mappings, which is consistent with the observed data. I will briefly explain the joint optimization and you can read our paper for more details. So imagine you need to do joint optimization for a batch of 3 spans. First, for each parent span, we identify all the candidate mappings which satisfy constraints. The idea is to construct a graph with these candidates and identify a maximum independent set of vertices from that graph which represent the final mappings. A maximum independent set is the biggest set of vertices that do not share any edges between them. So first, we construct a graph where the vertices of that graph represent these candidates and assign a score to each vertex corresponding to its likelihood as per the time distributions we constructed before. Now we add edges between candidates of the same parent span, since each parent span should be mapped to only one solution. In addition, we add edges between those candidates that share the same child span, since the same child span should not be attributed to more than one parent span. Now we use an off-the-shelf solver to identify maximum independent sets in this graph. If there are many sets, we iterate to find the one with the highest score to maximize likelihood. At the end of this process, we obtain the fully mapped traces. Finally, putting it all together, this is how TraceWeaver operates. First, we collect test spans in our developer environment and pass it to the call graph inference module, which outputs the call graph and the constraints. This is a one-time pre-process phase. Then during runtime, we collect live spans and run a suite of techniques to output the fully mapped traces. This is the reconstruction phase, which is an ongoing phase. Now we'll briefly run through some evaluation. Our basic approach is to evaluate trace reconstruction accuracy across increasing load, which creates high concurrency and therefore difficulty in mapping. In this experiment, we evaluate the accuracy on traces collected from 3 benchmark microservices. As you can see, TraceWeaver is able to get much higher accuracy compared to the baselines. Our baselines tried different strategies to solve the same problem. WAP5, for example, tries to build a service dependency graph where it tries to learn which service depends on which other service. We modified that algorithm to operate at a request scale, which maps child requests to parent requests in a greedy manner. vpath is another baseline, which tries to look at which threads handle the incoming and outgoing spans to identify mappings. This system works only for certain threading models and can be very inaccurate when threads hand off requests between each other, like done in gRPC. We also construct a strawman FCFS baseline, which assigns parent requests to child requests in FCFS order. Finally, we also show a curve for a variant which we call TraceWeaver top K, where TraceWeaver outputs K different mappings for each incoming span, and we mark it to be correct if at least one of those mappings is correct. This can be very useful for operators who do not mind iterating through K different options while debugging. This variant naturally exhibits even higher accuracy due to the relaxed requirement. We also evaluate on a dataset from the Alibaba cluster where traces are collected from production applications. The y-axis shows box plots which represent the accuracy distribution across the 15 most popular call graphs, with increasing load on the x-axis. Please note, since these traces are from a production environment, they are highly sampled, which decreases the concurrency that we see. Therefore, we artificially increase the load by post-processing these traces cleverly while respecting the original service delay characteristics. More details are on the paper. Now, as far as the results go, you see a similar degradation in accuracy as load increases for all the techniques, but TraceWeaver is still able to get usefully high accuracy, which can be utilized for many use cases, as we will show. We also evaluate in cases where there is call graph dynamism. We define dynamism as the case where there's a discrepancy in the normal call graph we found during analysis and the different call graph we see during runtime. Here we illustrate an example where dynamism occurs due to caching. So as you can see, there's a missing span during runtime because the response was cached, leading to the service not making that backend call. To handle such cases, we add fuzziness to our algorithm, which effectively tries to respect the call graph as much as possible, but allows for such discrepancies. The details are on the paper, but the plot on the right shows that TraceWeaver still gets pretty high accuracy. Now we describe a few use cases highlighting how imperfect tracing can still be very useful. The first use case is about debugging performance outliers, asking queries like which service contributes the most delay to the slowest 2% of the request. Now, without end-to-end tracing, a developer can only employ span-level analysis, which can only identify the spans which were in the top 2% latency at each individual service. The key point is that without tracing, there's no guarantee that the requests with the top 2% latency at each service need to be in the overall top 2% of the request. The y-axis here represents response time distributions, and the x-axis represents the different services. You can see that the developer view is very different from the ground truth. Now on the right side plot, we can reconstruct traces and plot service level time distributions of only those spans that we identified to be in the overall top 2% in terms of latency. Even though it's slightly imperfect, we're able to see a very close match with the ground truth. Now with this analysis, we can clearly see that the reserve and profile services need to be fixed to improve performance of the slow requests. Another use case is A/B testing, which evaluates if version B of a service improves or regresses performance. This test is usually done by sending a fraction of traffic to version B, as in the figure, and analyzing the metrics. Now in a system without tracing, it's unclear whether request 1 in the figure hit version A or B, making accurate comparisons difficult. So without tracing, all you can do is compare metrics of requests when they were just being sent to A with the metrics collected when requests were being sent to both A and B. With TraceWeaver, you can more precisely trace requests, so you can more directly compare both versions. Also, for context, in an A/B test, the way it works is you apply a t-test on the two sets of metrics to get a p-value. A lower p-value implies more statistical significance, but requires much more metrics data to be gathered. As you can see the plot, without tracing, which is the blue curve, almost 20% of traffic must go to B to achieve the required p-value. With TraceWeaver, which is the green curve, only 2% of traffic needs to be redirected to B to achieve the same statistical significance. So essentially with TraceWeaver, even at 90% accuracy, much less traffic can be sent to version B while still getting statistically significant evidence, which is great because if version B is bad, we're exposing fewer number of clients to that version. So, to conclude, here we present TraceWeaver, which uses information that is freely available to reconstruct traces with high accuracy and use those traces to answer performance queries. Thank you everyone for paying attention to this talk.